All right, so now let's move on to our next category, and these are the reactions of esters as well as carboxylic acids. We are sort of already covered carboxylic acid reactions in the first lecture. I just want you guys to have esters and carboxylic acids kind of in the same place in your brain. They have very similar reactivity and undergo very similar reactions. So first of all, how do we create esters? So some of the methods that we've already learned about to create an ester would be to use starting off with a carboxylic acid and then deprotonating it, right? So all that base is really going to do is form a carboxylate ion. This carboxylate ion can react with an alkyl halide in an SN2 type mechanism, right? So remember that those carboxylate ions are weak bases, but pretty good nucleophiles. So we can have this nucleophilic substitution reaction. That'll be one way to generate an ester. Another one that we just learned about is by taking your acyl chloride, starting out with something more reactive, going less reactive. All you really need there is an alcohol. And then we have pyridine in there to mop up the HCl that's created. That'll also be a way to generate an ester. Okay, so now for the new reaction. This is called a Fischer Esterification reaction. This is going to be the most important reaction of this sort of lecture here. And that's a way to convert from a carboxylic acid to an ester or back again. Okay, so these reactions are readily reversible. Okay, what that means from like a free energy standpoint, if we draw our free energy diagram, is that both of these sit pretty much at the same place in terms of their free energy. So you can go one way, but you can also go the reverse direction fairly easily. Okay, the way that you sort of tune this is if I really want to generate the ester, I would start with an excess of the methanol, or maybe or I could remove the water as it's formed, right? So that's going to be the method that we use in order to push this reaction in one way or another. But in terms of the mechanism, everything's going to be readily reversible. Okay, these reactions are catalyzed under acidic conditions, right? So I'm going to start with a carboxylic acid. I'm going to use an alcohol, and that alcohol will substitute for that hydroxide group. Mechanism. So I bet you guys could do this all on your own without even looking, but let's just go through it here. What's going to be the first step when we have these carboxylic acid derivatives under acidic conditions? Protonate that carbonyl oxygen, right? That makes that carbon at the base, that carbonyl carbon, even more electrophilic. So now I'm going to have nucleophilic attack on that carbonyl carbon and kick that pair of electrons up. This generates what? A tetrahedral intermediate. Okay. Now currently, the best leaving group here is that protonated methyl group, right? So what might happen often is this guy comes back down and kicks that off. But again, that would be an unproductive step, just taking us right back to where we were. The productive thing is going to be to get rid of one of these groups here. Currently, it's not a good enough leaving group though. So the first thing I got to do is I got to make this one a less good leaving group. This one here needs to be a less good leaving group. I can do that by chopping off that hydrogen, proton transfer. Likewise, this needs to become a better leaving group. So how do we do that? We're going to have to protonate it, right? We're under acidic conditions. So the first step here is going to be to deprotonate this leaving group, or this group here, so it's not our group. And then likewise, we're going to have to, the goal is really to chop that guy off there. So that's going to happen by our acidic conditions protonating that oxygen. So now I have my tetrahedral intermediate where the best leaving group is what I actually want to get rid of, right? So this would be the productive way to do it. And so now this pair of electrons can come down and kick that back off. We get to the point where we now have our protonated carbonyl oxygen, And that's all well and good, but we want it to stay here. We don't want it to go into the reverse direction, right? So we're going to do that by deprotonating that oxygen, leaving us with our ester. Okay, so here we started off with a carboxylic acid. Since it's acidic conditions, we first had to protonate that carbonyl oxygen. This generated our tetrahedral intermediate. And the next few steps, these steps here, were all about converting the, getting our tetrahedral intermediate so that the best leaving group was the thing that we actually want to kick off. Okay. And then we have our esters. So then again, you guys should be able to give me the reaction mechanism for the exact reverse direction as well. That's something that you guys are going to be doing in your discussion for this chapter. Okay. But again, readily reversible reaction. One of the big pieces of evidence for this mechanism is the fact that if we isotopically label our alcohol and toss that in with our carboxylic acid, the isotopic label is kept for the ester as well. Okay, so that's how we know that that oxygen is actually being incorporated into this molecule. And again, as I said, these reactions are readily reversible. So how do we make sure it proceeds in the direction that we want? We either use an excess of methanol and then remove the water that's being formed, or even better, we do both of these, okay? Likewise, just to sort of think, what if I wanted it, what if I started out with an ester and I really wanted a carboxylic acid? Well, then you're gonna start out with an excess of water and make sure to remove the methanol as it's being generated, right? So this can go in either direction. All about what it is what's your desire? What are you trying to form? Okay, so this is now another method of going from an ester to a carboxylic acid, but this one's going to be an irreversible method. Okay, so the Fischer esterification can be used to go in either direction. This method right here, which takes place under basic conditions, right? Fischer esterification was acidic conditions. Under basic conditions, esters will hydrolyze, and this is what's called a saponification reaction. Okay. Yeah, again, just important to consider that this is going to be irreversible, and we'll see why that is here in a second. Okay, so what do we do what's our first step under basic conditions? It's just nucleophilic attack. That pair of electrons jumps up there. We form our tetrahedral intermediate. Now we ask ourselves, do we have a good leaving group? In this case, these two are pretty much equivalent leaving groups. We're both going to, in both cases, we generate an alkoxide ion. However, if I did it this way, that would just take me right back. Oh no, I lied. That's the way we want to go. If I did it this way, that would just take me right back to the beginning, right? So although that may happen, again, you can sort of think about it, out of every 100 tetrahedral intermediates formed, maybe 50 do take this back step, but that just gets you right where you started and you can proceed forward. So instead, the sort of productive way would be to have this pair of electrons come down and kick off this particular alkoxide ion. Then I'm left with my carboxylic acid, okay? But the thing that makes this reaction irreversible is that when you get to this step here, this is a way better base than a carboxylate ion. So the last step is going to be proton transfer from this alcohol, from the carboxylic acid to the alcohol. And this reaction cannot happen in the reverse direction, right? This is not strong enough base to reach out and grab and deprotonate an alcohol. It's just not a strong enough base. So that's what makes this reaction irreversible, is this last step here. When you have the carboxyl, carbon stops being electrophilic because of the presence of this negative charge here, right? Electrophilic species are electron deficient. There's a lot of extra electron going around between those two bonds, right? So again, this is just an irreversible way of creating a carboxylic acid from an ester. Okay, so again, this is readily reversible. You should be able to draw mechanisms in both directions. We can create a carboxylic acid from an ester, but we can also create an ester from a carboxylic acid. This, the saponification, is irreversible. You can only go in the one direction. Okay, so now how do we create an amide from an ester? Well, this is an example of going from something that's more reactive to something that's less reactive. So we can do this without any sort of a catalyst. All we really need is to have an amine mixed in with an ester, and that will create an amide, right? So we can go from something more reactive to something less reactive pretty easily. It is a slow reaction, but it can happen, and we should be able to do the mechanism for it. In fact, this is going to be a mechanism that you guys do all on your own, okay? Other reactions of esters. Lithium aluminum hydroxide, what does that do for us? It's a reducing agent. It can reduce an ester all the way to a primary alcohol, okay? And this mechanism is going to be basically identical to what we saw with the acyl halides, where we're going to use an excess or really 2 rounds of lithium aluminum hydroxide to complete this. Okay, so yeah, I mean, I'm going to breeze through it. Hopefully you guys have this down, right? What do we think of when we think of hydrides? We think of nucleophilic hydrogens. So the hydrogen is doing a nucleophilic attack. We get to our tetrahedral intermediate. We have this good leaving group that gets kicked off that creates an aldehyde. Aldehydes also react with lithium aluminum hydroxide. This creates a new tetrahedral intermediate, which does not have a good leaving group. So then the only thing we can do from there is to protonate it. Okay. Likewise, we have Grignards reacting with our esters exactly as we saw before. 2 rounds of addition. Okay. Actually, before I go on, I do want to say one thing, make a note. Carboxylic acids and carboxylic acids and esters, I said to keep in the same place in your mind because they undergo similar reactions. That said, they're not always identical. So for example, here, if I tried to do the same thing with excess R, Mg, Br, this would not work, right? And why is that? Because our Grignard can play the role of a base as well. So instead of having our Grignard attack the carbonyl carbon, it's just going to pull off this proton here. And so really what I would be left with would be a carboxylate ion. And whatever that R group is now has a hydrogen put on it, right? So let's just be more specific here. Say excess CH3 MgBr. All we're going to really create is CH4, where this hydrogen now makes up whatever that missing hydrogen was, right? So carboxylic acids will not react, with Grignard reagents. Grignard reagents you can't use in the presence of even like a protic solvent like water. Okay. We do have a method. So we used lithium aluminum hydroxide to reduce an ester all the way to a primary alcohol. Well, what if we wanted to stop at that aldehyde step? For this, we would use this sort of special reagent, DIBA, which only has 1 hydrogen that can be donated. So 1 nucleophilic hydrogen. It's very similar to lithium aluminum hydride, but has those big bulky groups. So it will step. We had something very similar for acyl chlorides, which was, aluminum with 3 OR groups and then a hydrogen. So it was lithium aluminum. These are very, very similar. They both do the same thing, which is you only have 1 round of reduction and they stop at the aldehyde step. For whatever reason, This particular reagent is unique to acyl chlorides, and this particular reagent is unique to esters. So they're doing very similar things. They both look very similar. They got big bulky groups coming off of the aluminum. One of them specific to esters, one of them specific to acyl chlorides. So unfortunately, they're very similar, but we got to make sure to make that distinction.